Hi there guys, well welcome back. We've just done 3i and we're going to work towards 3j in this video. 3i was mostly about the division of polynomials using the technique of long division. In 3j there's a lot here, there's a lot to unpack. We're now talking about the remainder theorem, we're talking about the factor theorem, and then on top of that, if that wasn't enough, there's also an algorithm from Horner, so Horner's algorithm, or what we also call synthetic division, which is essentially another way of doing polynomial division. So we're going to learn how to do that as well. Now, there's only actually 2 examples in this exercise, but really there's a bit more which we need to unpack about the factor theorem and the remainder theorem, or what they're calling the polynomial remainder theorem here. Now, they start off with let's get rid of that. They start off with the remainder theorem. I'm actually going to start with the factor theorem here. And I've just copied this one onto here. And it tells us that if you've got a polynomial, so, this could be a quadratic, cubic, quartic, or higher powers. If you've got a polynomial, and they're just saying that our AKs are real numbers, so our coefficients of all of our powers of x are real numbers. And it says the first one cannot be equal to 0. The others could be equal to 0. But there you go. It says that this has a factor of x minus p. P belongs to the real numbers if and only if f of p is equal to 0. Okay, so we need to unpack this a little bit. And it's essentially saying that this, remember, f of x there is equal to, now remember the format which we had last time round. If we had our g of x, which we're dividing by, then you get your quotient and then your plus remainder, the remainder. But if this thing is just a factor, then there won't be any remainder. That's the first thing to say. So we should have this format here. Now your g of x is just your divisor, and so that's this factor here. So it's a factor or divisor. And so really what we're normally saying is f of x can be divided by g of x to give us this quotient of x, to give us the other factor. Okay, so this is our factor, and we're being left with this other factor. Now I've just written it in that form, just as you saw in the previous exercise as well. Okay, so f of x is equal to, and I'm going to put the divisor as x minus p, and then we've got our quotient of x here, and that, in this case, when we have this as our polynomial, that would be an times x to the n minus 1, because when we times that by this, we'll get this thing here. And then there'll be lots of other coefficients, and not necessarily the same as these coefficients here, but that first one is the same. And this will be a polynomial order 1 less. Okay, so say, for example, if this is a to the power of 5, this is a quintic, then this would be a quartic to the power of 4. Okay, so, I mean, what is this factor theorem saying? It's saying that if you put in p for x, so now if we say fp, we'll notice that you're going to get p minus p on the front here, times by this an x to the minus 1 plus blah, blah, blah. That's our quotient. Then, of course, this becomes 0. So f of p becomes 0. Okay, so it's saying, essentially, if there is a factor of x minus p, then when we put p in, so let's think about that. If we had a factor of x minus 2, when we put in 2 into this original function, you get a 0. It's true the other way around as well, which is why they say if and only if. If and only if in mathematics is not just leading one way, it's also saying it goes backwards as well. So the implication goes both ways. It's saying if you have f of p is equal to 0, then when we go up through the steps, we can see that x minus p must be a factor in this case. Okay, so let's just have a look at how we use this one, because the book doesn't really go into using this particularly. And so let's come up with an example here. And let's say we've got f of x is equal to x cubed minus 7x and then minus 6. Now, I'm going to tell you that this factorizes and it has 3 linear factors. So in other words, there's 3 brackets here where we've got x, let's say minus a, and x minus b, and x minus c there as well. So we've got 3 factors. Okay, I could have called them p, q, and r to be a bit more consistent with this, but I haven't. I've just called them x minus a, x minus b, and x minus c. Now, I can use this theorem backwards by saying, let's make choices for p to see if we get a 0. And if we get a 0, that will mean that x minus p is one of our factors. Okay, so what choices could we make? And there are sensible choices which we could make here, because we definitely know that when we times these 3 things together here, we end up getting minus 6. Now, how do you get minus 6 from 3 integer numbers? And in this case, I'm assuming that these linear factors just have integer numbers and there's no coefficient in front of the x as well. Or in other words, the coefficient of x in each case is 1 to give us that 1x cubed there. So what 3 things times together to give minus 6? Well, you know that possibly you could have a 1 involved there. Possibly you could have a 2 involved, possibly a 3, and possibly a 6, because those are the factors of 6. So clever guesses as to what this A, B, and C could be would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Because we don't know, we could have, for example, I don't know, we could have 1 times by minus 3 times by plus 2 would give us the minus 6 there. So it's got to be 3 out of these 8 things here. And it may be that one thing is repeated. So for example, you could have a 1 times by 1 and then times by minus 6. So there could be a repetition of something. Okay, so what we're going to do is actually try here. Let's try some guesses and let's put in f of 1. So if we put 1 into here, we're looking for to see if x minus 1 is one of those factors. So we are trying to find the factors, not by a process of a division of polynomials, but simply by making some guesses and substituting those numbers in. So, for example, we'll have 1 cubed, take away 7, minus 6, and we can see that that is not giving us 0. And since that is not giving us 0, then x minus 1 is not a factor. Okay, well, we can try another one then. So let's try minus 1. When we put in minus 1 cubed, we're getting minus 1, of course, and then we're putting in 7 lots of minus 1, which is going to give us plus 7 there. Minus 1 plus 7, and then we've got the minus 6 on the end. And we can see that this is giving us a 0. And since it's giving us a 0, that means, since it's giving us a 0, that means that x plus 1, so minus minus 1, is a factor. Okay, so now x plus 1 is a factor. That might be another factor here as well. So let's try another number. So as I said before, it could be, we've got 1 times by 1 and then times by minus 6. Well, let's just move on to the 2's for this one. And again, we're making some guesswork here. So we're saying f of, I'm going to put in minus 2 here because it wasn't very successful when we put in the positive number earlier on. Let's just try this one. I'm going out of order here. I think this is the factor, you see. So I'm skipping a step. So we'll say here minus 2 to the power of 3, minus 7 lots of minus 2, and then minus 6. So that's giving us minus 8 and plus 14 and minus 6. And yes, I can see that one's giving us 0. So that means to say that x plus 2 is also a factor. Now, if I found 2 of my factors, it's very easy to find my other one because I know that I've now got x plus 1, one of my factors, x plus 2 are one of my factors, and then I've got x is minus 3 as my other factor, because this, and this, those n numbers need to times together to give minus 6. So this one comes out really easy, and of course I can put 3 in here to check that one out. So 3 cubed is 27. Take away 21, take away 6, brings us back down to 0 as well. Okay, so what we've done here is a process of finding our factors after being told that this thing does factorize and that there's no remainder. And we've found our factors by doing really some guesswork, some sort of clever guesswork using the factor theorem. Now, that's not explained in the book, but obviously you could be asked for an exam question. Can you check, for example, that x plus 1 is a factor? And to do that, you would need to substitute in the minus 1 to check that you get a 0. If you get a 0, then it is a factor. But this method can be a kind of an alternative way of finding factors for polynomials rather than doing the division of polynomials. Okay, so let's have a look at the polynomial remainder theorem here then. So the remainder theorem is kind of an extension of this one. And remember that if we had f of x was our function again, remember from the previous chapter we wrote that as f of x equals g of x times by our quotient of x plus this remainder. Okay, so what we're really saying is if we divide f of x by our divisor or by our factor, in this case x minus p, then we should be left with q over x and this remainder which we are yet to divide by the factor. Okay, so that's just the format from last time round. If we do a division of polynomials, we get a quotient and we get a remainder which is yet to be divided by our factor or our divisor. Okay, so this is another format for this thing here. Now, the polynomial remainder theorem is saying, okay, well, what happens if x minus p is a factor? Well, that's going to replace our g of x there, so we can write x minus p times by the quotient of x, which is of order 1 less than f of x, of course. Okay, because, you know, say for example, this is a quartic, then this must be a cubic in order to get a quartic out by timing by the x. And then we've got plus the remainder on the end here. And the remainder is not a function of x. I'm not going to write r of x here because I know that the remainder is always of degree 1 less than the divisor. Okay, and that's what we learned from the last exercise as well. Okay, so given this format here, it's really easy to show polynomial remainder theorem because the remainder theorem says that, let's just read it out. It says, given this polynomial and a real number p, then the remainder when f of x is divided by our linear expression x minus p is f of p. Okay, so the remainder is f of p. Also, let's just substitute in p in this case and see if that's true. Well, f of p is going to equal to p minus p times q of p plus r. Okay, now p minus p rather, is going to give us 0, and then times by q of p, and then plus r there as well. So you can see that this is disappearing and we're getting f of p is equal to r. Okay, so we've done the factor theorem and the remainder theorem. We're just going to leave those where they are for the moment, and then now we're going to come up with another technique for division of polynomials. And this one, as I mentioned earlier, is called Horner's algorithm, or it's called synthetic division. Okay, and in order to do this one, we're going to take the same example which they've got in the book. So we're going to take this f of x is equal to 3x cubed minus 2x squared minus 5x and minus 1. Now, in order to perform this algorithm, we're just going to write down this in a different format. And what we're going to say is we've got 3x minus 2 times by x minus 5 times by x minus 1. So now when we multiply this out, you can pretty easily see that this alternative format here is giving you 3 lots of x cubed. So it's going to be this times this times this gives you x cubed. And there's only one way of getting out x squared, and that's going to be minus 2x times by the x here as well. And there's only one way out of getting out the x, and that's minus 5 times by x. So this is a nice little different format for writing out our polynomial. And we can do that with any polynomial, of course. Now, if you just want to check this, obviously it's just a little bit of algebra to check it. We're saying 3x squared minus 2x minus 5. Now that's times by x, minus 1 on the end. And when we times everything by x there, we're getting 3x cubed minus 2x squared minus 5x minus 1. Now, you might want to have a little practice with this just to write another polynomial in this format, just to see that it works, just to try and get that yourself. Now, if you know that, frankly, you don't really need to know this table method. However, in an exam situation, they could say, can you use synthetic division? And they might be expecting the table method. So the table method is essentially going to use what we've just found out there. So using this alternative way of writing out f of x, we can now think about doing a division by x minus p. So for example, if we want to do division by x minus p, well, we can get our remainder by putting in p in here. So remember, remainder theorem tells us that if we do f of p, we end up getting r. So putting p into here can be a little bit more work than putting p into here. In fact, what's nice about this is later on you'll see that you actually get out your quotient as you go as well. But we'll come on to that later. So there's actually another reason to do this too. So sure, you could put your p into here, no problem. But if you put your p into here, not only is it slightly quicker to do, it also later on shows you what your quotient is. Okay, so for example, if we take this one back, if we say we're dividing by x minus 2, and that's what the book chooses as well. Yeah, so we're going to put in f of 2. Okay, so we're going to put f of 2 into this thing here. And what we're going to do is substitute the 2 into here. So we're going to say 3 times 2 minus 2 times by 2 minus 5 times by 2 minus 1. Okay, so that's the process which we're going to do. Now, if we do that, we'll end up getting 3 times 2 minus 2 gives us 4. 4 times 2 minus 5 times 2 minus 1, and then 4 times 2 is 8. 8 take away the 5 is 3, and then 3 times 2 minus 1 gives us 5. So the remainder is 5. And you can see from their little algorithm here, the little table, that they're giving you the same thing. Okay, right. So let's just take this and see what they're up to with this synthetic division method. Now, it should be noted that they've made a mistake in here. And they've made a mistake here because they've put brackets around here. And obviously that will be corrected in newer copies of the book, but there should not be brackets there and there. And you can see that that makes sense in the next line. So that's a little mistake in the book. Okay, so what's happening? So this is exactly the same as what's happening here to get out the 5 and get out the 5 there as well. So let's just set this one up. And in fact, let me copy across. Let me just copy off the hint, and then I'll make this in real time, and then you can see how it's done. So our polynomial, if you remember, was f of x is equal to 3x cubed minus 2x squared minus 5x minus 1. That's what we're starting with. Now for us, we're going to write down the 3, the minus 2, the minus 5, and the minus 1 at the tops of our columns. And then underneath these ones here, we're going to write down plus. So plus, plus, and plus. It's good if you write that to start off with. Now, since we're trying to divide by x minus 2, that means to say that our p is equal to 2, and what we're trying to find out is what is f of p. Okay, now f of p is substituting in p in here. Remember, I just get rid of those brackets again because they're wrong. Okay, so we need to substitute p into here. So we're going to substitute in p, and we're going to write that on the side here. And you'll notice that every time that you're dealing with x, in which case that's 2 here, so that's f of 2. Sorry, I should have said f2 there. What we're looking for. Every time we substitute in 2, we're actually timesing by it in this format. Times by 2, times by 2. I'm going to put a times there over to the side. Okay, now the first thing that you do is you times by the original coefficient of x cubed, of the highest power of x. So let's bring down this 3. Okay, so we're going to bring down the 3. And now we're going to times the 2 by the 3, and that's going to become our plus 6 up here. Okay, so plus 6 is simply saying that what do you get out from doing 3 times by 2? Okay, now we need to minus the 2, and the minus the 2 is here, so we really just need to add these 2 here. If we add those 2, we can see we get 4. Okay, so 4 is now at this stage here. The next thing that we do is times by x again. So times by this thing over to the side. So 4 times by 2 gives us the plus 8. And once we've done that, we need to minus the 5. So minus the 5 is the same as adding these two things here. Minus 5 plus 8 gives us plus 3. In fact, I don't need to write the plus 3. I'm just saying 3 there. Same process again. We've now got down to this stage here, and we need to times by x again. So times by x is going to give us 3 times by the 2 there, which is going to give us 6. So we've got plus 6 there. And then finally, we're going to take away the 1, and that will give us f of 2, and f of 2 is 5. So 5 is the remainder, because we know that f of p is equal to our remainder using the remainder theorem. Okay, so 5 is then equal to our remainder in this case. So we've now found out what the remainder is. Now, a little bit more than this, this method actually tells us what the quotient is as well. So we can now write down f of x is equal to our, and I'm going to write down the divisor first of all, so x minus 2. Then I'm going to write down my quotient, and then I've got my plus 5 on the end. Now, this is the beautiful part of this method. This is also giving you our quotient in these numbers here. Reading from left to right, we've got 3 lots of x squared, so that's this one here, plus 4 lots of x plus 3. So the method is giving us our quotient. Now, this is really just the same as doing our division of polynomials. It's the same thinking that's going on there. It's the same calculations which are going on for each of our lines in our division of polynomials. And we're getting the same numbers out, and we're still getting out our quotient. It's just a more efficient way to write it down. But we never proved that the division of polynomials through the long division technique actually worked. And we're not proving here that this works either. But the two situations are analogous. This is just an alternative method. And you could be asked to do a division of polynomials through long division, or you could be asked to do it through synthetic division. Both the same thing. It's just that this method here, in other words, Horner's algorithm, is slightly quicker. And it relies on us knowing that f of x can be rewritten like this. Now, there's a lot to unpack there. There's a lot of learning to do, and this is going to take quite a bit of practice to get this one right. So not only have you now spent a couple of hours practicing your division of polynomials using long division, you're now going to need to practice quite a few times through, probably a couple of hours again, this kind of thing. Now, this is doing it once. If you then need to divide it again, so if you need to do another division of polynomials, say now you need to divide this quotient by another factor and get another remainder, or potentially no remainder at all, then you can do this process again. So sometimes we do this in multiple steps, and you'll see that in a later question. Okay, now if you want to skip on to the next question and you're just interested in doing the technique now, then by all means skip on in this video. But what I want to do as well before we get to the next question is just show you that this is the same as doing the long division technique for a division of polynomials. And I also want to just make some sense of this as well as to this big question: why is this quotient turning up in these numbers here? We've explained why the 5 is turning up. The 5 is turning up because of the remainder theorem. Because when we put in the 2 there, we can see that we've divided by x minus p, and we're ending up with the remainder, and that's from the remainder theorem. So that's easy. But why we're getting out this is the quotient is a real head scratcher. So what I'm going to just try and do is show that this is the same as doing the long division by the division of polynomials by long division, and also talk about why this is true as well, and why our calculations, why these calculations are leading to this quotient. And in doing that, I'm going to actually use another method of comparing coefficients on both sides. So, okay, so I'm going to do that thing again. If you want to skip forwards a little bit, you can do. Okay, just taking a little bit there. So I'm going to do my whole thing again here. We'll just try and write this kind of small. We're saying f of x is equal to 3x cubed minus 2x squared minus 5x minus 1. And our synthetic division, if you want to just remember how we did this again, we did 3 minus 2 minus 5 plus 1. And here we're dividing by our 2, so I'm going to put a times by 2 there, dividing by this factor of x, not divide, but x minus 2. Okay, so we need to substitute 2 in. So now what do? We bring the 3 down. We need to remember to put pluses just underneath each of these things here. And we bring the 3 down, and we're doing 3 times 2 is going to, first of all, give us our first plus. So we're going and following this diagonal here, and that's going to give us plus 6. And minus 2 plus 6 gives us plus 4, times by the 2 gives us 8, minus 5 plus 8 gives us 3. So that gives us our 3 here. And now we're doing 2 times by the 3 to give us this number up here, which is 6. Okay, and then we're getting 1 plus 6. Sorry, it should be minus 1 there at the top. Minus 1 plus the 6 gives us plus 5. So this is our remainder in this case. Okay, now let's look at the situation where we're doing a long division here. So we've got 3x cubed. That's meant to be a cube there. And 2x squared minus 5x minus 1 divided by this x minus 2. We say x into 3x squared of 3x cubed gives us 3x squared. Okay, times the two things across, and we're getting 3x cubed, and then we're getting 3 times minus 2, which gives us our minus 6x squared. Now you can see that the 6 is the same as what's turning up here, but whereas we add these two things together, here we're actually subtracting these two things. And when we subtract those two things, we end up getting a plus 6 here. Okay, so the other term cancels, and we end up getting 4x squared. And that's the 4 which is turning up here. Now, when we're doing x into 4x squared, we're getting plus 4x. And so 4x times by this thing here gives us 4x squared minus 8x. And let's bring down this 5 minus 5x here. And when we take those two things away, the minus 8x is going to become a plus 8. And that's this number here. So we've got an answer of 3x here, just like we've got here. And when we do x into that 3x, x into the 3x there gives us our plus 3. So we're getting now 3 times by this thing here. And so 3 times this gives us 3x, and then minus 6. Bring the minus 1 down and do our subtraction. Sorry, I'm messing that one up a little bit there. Bring the minus 1 down there. Sorry, we should have put the 3x minus 6 there. That was from doing the 3 times by this thing here. And then the subtraction of those gives us, let's try and write that a little bit smaller, 3x minus 6. And the subtraction of those two things there gives us 5, which is our remainder again. Okay, so that's the same as this 5 here. So you can see that the steps are exactly the same, except for this takes a lot more time writing out, but there's the same thinking which is going on. Each time there is the same thinking, and there's the same work which we are doing with each of these numbers. Okay, so the two situations are completely analogous. Now, that doesn't prove that this is going to be the quotient or that this is going to be the quotient. And that's really much more tricky to figure out why the quotient is coming out from this process. Now, I suppose you could set this thing up as saying instead, we have our, let's say, again, we've got 3x cubed minus 2x squared minus 5x minus 1. And we could set this up as equal to ax squared multiplied by x minus 2 plus bx times by x minus 2 plus c times x minus 2. Now, where has that come from? That's come from me saying we've got ax squared plus bx plus c multiplied by x minus 2, our factor. And then what we're forgetting here is our plus r. And r in this case is just going to be a constant term on the end. Okay, so where's this coming from? This is coming from us saying f of x equals q of x times by g of x, our divisor, plus r. Okay, so from this, I've created a quotient which will give us an x cubed term by timesing by this. But we know the quotient needs to be a quadratic. We know that the remainder has a power 1 less, a degree 1 less than the divisor. So this is just a constant term. Okay, and then what I've done with this is I've multiplied that out to give us ax squared times by x minus 2. So we're doing this times by this and so on. Okay, bx times by this is this thing here. So what I'm going to do is just take all of that back. Okay, take all of that back there just to get rid of that one. Good, get rid of all of that. And there's a plus r, which is missing there. Okay, sorry about this, but I'm just trying to fit everything onto one page there. Okay, so this is really what we're trying to solve here by comparing what's going on each of the sides. So now, for example, if I look at x cubed, okay, so we look at x cubed, we can see by comparing coefficients, 3 has got to be equal to a. So the thing on the left-hand side is equal to the thing on the right-hand side. There's only one way of getting out x cubed here, and it's by doing a times by x squared times by the x. Okay, now let's look at x squared. Well, when we look at x squared, we can see that there's two ways of getting that. We can see you can do ax squared times by the minus 2. So we've got x squared times by the minus 2. So that's minus 2a lots of x squared. But we can also get out on this side bx squared. So we've got bx squared, so it's bx squared on this side here. And they're the only two ways of getting out an x squared. Now that's equal to minus 2. Okay, so we can compare that. We can try and solve that by putting in the 3. So we've got the minus 6 there, and minus 2, and there's b. And so b needs to be equal to minus 2 plus 6, which is giving us 4. Okay, so you can see that in solving this equation, it relies on us knowing what a is from the previous part. And that's exactly the same as what's happening here. First of all, we get out a. Okay, and then once we found a, we need to solve minus 2, take away this, so plus 2 lots of a. Plus 2 lots of a because we're plus 2 lots of a because there we go, there's our plus 6. We had a minus 6 there. So the solution of this equation here is telling us what b is. So this is essentially solving equations as we go through. And each time round, each next coefficient that we're looking for depends on the previous coefficient and the next one from the quotient. So what does that mean? Well, let's look at x to the power of 1. Well, we see that x to the power of 1 here is minus 5 on the left-hand side. Okay, I put that on the right-hand side here, but it doesn't matter. Okay, so minus 5. And there's only two ways of getting out an x term from this expansion. It's from minus 2 times by bx. Okay, so I've got minus 2b there. And it's from cx, so it's c. Now I can obviously times both of those things and this side by x as well. But I'm just looking at the coefficients and I'm comparing coefficients. Now I need to solve this equation. So c is equal to minus 5 plus 2 lots of b, which is 4. And that's exactly what's happening there. Okay, so it's the solution to this equation. So each next coefficient that we're looking for in the quotient is dependent on the previous coefficient. So c there is equal to 3. Okay, and so for the next one to find the 5, again we're looking at the next term. So we're looking at x to the power of 0. There's only two ways of getting that from this expansion. It's by doing minus 2c there and the r. So we've got r minus 2c. Now look, every format has been the same here. Okay, so it's the same process each time, which is what this is talking about, the same process each time. So now the coefficient of x to the 0 on the right-hand side here is the same as the coefficient on this side, which means to say that r is equal to minus 1 plus 2 lots of c, which is exactly what we're getting out here. C was equal to 3, which means that we're getting out plus 5. Okay, now obviously this is not a proof as well. I mean, it would be a proof for a cubic being divided by a linear term which is just x minus p, so there's no coefficient of a there. It would be a proof if I'd have put in x minus p, and of course it would be very easy to change this to x minus p to show that that's the same thing that's happening in this case here. It would be a proof in that case, but then how's it a proof for x to the power of 4? And either we'd have to do this, or maybe we could do some proof by induction by taking it to the next level to show that each next coefficient is always dependent on the previous coefficient, which we're trying to work out, which we've worked out before. Okay, guys, I hope that that's useful. Perhaps some people have completely skipped through this, but from my point of view, it was really annoying to notice that we had here 3, 4, and 3, as our quotient, so 3x squared, 4x, and plus 3. And likewise, the same here, there's our quotient, and to not understand why that's the case. And hopefully from unpacking this a little bit and trying to solve equations by comparing coefficients, we can see that, in fact, each of these situations is analogous. And each of these three methods is exactly the same thing, but you can see, of course, that this creates a ton of algebra. This still creates a lot of algebra, and this method creates almost no algebra. Okay, so there's our three methods, starting with this, going to this in terms of complexity there, but they're all interesting and useful methods which we would use in mathematics. Okay, right, so thank you for listening to that. And next we're going to do the last of the questions here before the exercise. And this time around they're saying use synthetic division to find the remainder when dividing by the g of x in each of these cases. So, okay, so let's see what we've got here. Let's just do the synthetic division. I know that this is the process that a lot of people are interested in, of course, and this is the process that you need to learn. And the understanding why it works is frustrating, but ultimately, you're not going to be asked to prove that the quotient is popping up in the synthetic division approach. You're just going to need to use it. Okay, now we're going to be dividing by x plus 2 here. So what we want to do is work out what f of minus 2 is. So we're going to put the minus 2 in here. So this is just our process. And remember, we need a plus there, a plus there, a plus there, and we take the 3 down here. 3 is just 3, and then that's the point at which we do our first diagonal. So minus 2 times by 3 gives us minus 6 there. So 11 minus 6 gives us 5. And I'm putting it in the wrong place. That's giving us 5 there. Okay, and 5 times by 2 gives us minus 10. Okay, and adding those two together gives us minus 17. Okay, and now the diagonal is times these two things together. So we've got now plus 34 and plus 34 minus 19 gives us, so take away 20 and add 1 is giving us 15. Sorry, I'm writing it in the wrong space again. And the 15 is our remainder here. So this is our remainder. So what we can really say here now is that we've got 3x cubed plus, so this whole thing here, just save a bit of time, is equal to x plus 2 multiplied by 3x squared plus 5x minus 17, and then plus our 15 on the end. So that is our division, leaving us with our quotient. Or if you like, what we can say is not just that f of x is equal to this, but we can say that f of x when divided by x plus 2 gives us our quotient, which is this thing here, and then plus the 15, which is yet to be divided by x plus 2. Don't put brackets on the bottom there. I'll put them on anyway. Okay, so that's what we've done, and we can then leave that as our final answer. It's not rubbing it out, so there we go. That's leaving it as our final answer there. And let's just check this one in the book. Yeah, we can see that we're getting 3 minus 5 minus 17, and you getting your 15 there. Now, guys, I'm not going to do the next one here because the next one is exactly the same process and it's just more practice with the same thing. But what's notable about the next one is that you can see that the numbers often get really large here. So as you go through, especially in this case, we're timesing by 5 in each of those cases, these numbers are getting really large. And that's fine, and that's quite common. Okay, I actually think there is one more question. Yes, there is, and this is really what I was looking for here. So for example 23, this is saying the polynomial is given here, and it's saying use synthetic division or Horner's algorithm to show that x minus 3 and x plus 2 are factors of the polynomial. So now these are two factors, and that's going to give us a third factor here as well. The third factor will hopefully have 2x plus or minus something at the end as well. Okay, so seeing as they're factors, we should have a remainder equaling to 0 when we substitute in, for example, 3. Now, I'm going to, consistent with the book, to do this in the same order as the book. The order which they've done is with this factor first and then divide by this factor. Now, you could do it the other way round and it would also work. But let's do it consistent with the way in which the book does this. So they've got 2, 1, minus 15, and minus 18 here. And remember, we're going to put plus, plus, plus. And then we're going to put in 3 here, so times by 3. Bring the 2 down. 2 goes there. And then 2 times by 3 gives us 6. Okay, 1 plus 6 gives us 7. And then 3 times by 7 gives us 21. 21 take away 15 gives us 6. Nice positive answers here. 3 times by 6 gives us 18. And then we can see we get a 0 on the end, and that's our remainder. So we can show, we've now shown, therefore, from this algorithm, we can see that f of 3 is equal to 0, and therefore x minus 3 is a factor. Okay, right. So that's what you would write to say I've shown that this is equal to a factor. However, I would do that aside because what we can do is go directly underneath this, because this is the factor, this is the quotient which is left, which we're now dividing by x plus 2. This is really 2x squared, 7x, and 6. That's our quotient. So we're going to divide our quotient now by the x plus 2. So I'm going to just put down a plus and a plus there. I'm going to put down a minus times by minus 2 here. I'm going to bring the first number down again. So I've got 2 there. 2 times minus 2 is minus 4. So minus 4, let's put it in brackets so it doesn't get mixed up with that plus there. So we've got 7 minus the 4 gives us 3. And then minus 2 times by the 3 gives us minus 6 there. 6 plus minus 6 gives us a 0. And now we can see that this is also a factor. And we should state, therefore, this is a factor. Therefore, it's implying that f of minus 2 equals to 0. Therefore, x plus 2 is a factor. Okay, is a factor. So that's what we should say to the examiner. Okay. So next part, it says B, hence fully factorize this polynomial. Okay, so fully factorize this polynomial. Well, we've now got our f of x is definitely equal to x minus 3 and x plus 2. And in our last term, we can see that in order to get 2x cubed, we've got to have a 2x there. And in order to get minus 18, we can do minus 18 divided by 2 divided by minus 3. And so that's divided by minus 6 in total. That's the same as saying 18 divided by 2 times minus 3. That's what I'm doing there. And therefore, that's giving us an answer of 3. It's giving us plus 3. And we didn't actually need to do that. The reason why we didn't need to do that is because the 2 and the 3, the quotient is actually there. So we've got that quotient again, and there it is. 2x plus 3 comes from this. Okay, so there we go, we're done. Okay, that's a fully factorized polynomial through a method of synthetic division by dividing by x minus 3 and dividing by x plus 2. Okay, now they've actually helped us out by giving us those two factors. If you were going to make a factorization and you didn't know what to divide by, then you're going to have to make guesses and clever guesses. And that's what I talked about right at the start of this video by saying, okay, well, what are our factors of 18? And let's think of using plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. Those are what can be in the end here. And then actually we're a little bit, what confuses things is that we end up getting this bracket here is essentially x plus 3 over 2 by factorizing out the 2 from the front. So we could have any of these divided by 2 as well. That actually comes up in the next exercise. Certainly 2 of the factors are going to be just whole numbers or integers. So we could make some guesses, some clever guesses, if we were asked just to factorize this thing and we didn't know where to start. And you can see that as soon as you've got to this point here, we find out that we've found one of our factors by substituting in plus or minus 2, in fact, substituting in minus 2. Okay, guys, well, thanks for that. Just a little bit extra on the end here. So a little bit extra is that the word algorithm, let's just see if we can search this one up. The word algorithm, process, or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. Now, if we say as well, where does the word algorithm come from, originate from, says the word algorithm is derived from the 9th century mathematician Muhammad ibn Musa al-Khwarizmi. Okay, sorry about the pronunciation there, but okay, I'll try my best. And it's Latinized, this al-Khwarizmi is Latinized to algorithm or algorithmi. Okay, so this surname of the 9th century mathematician has actually been Latinized to give us algorithm. Okay, and now obviously they didn't have, back in the 9th century, they obviously didn't have formal algebra. So this was just ways of solving equations, essentially, word problems by doing processes, by doing algorithms. Okay, so a little bit of cultural extra stuff there at the end. You're welcome. Okay, thanks for listening in, and good luck with the exercise, and I'll see you for the next one.